Hello, folks. All right, so folks, so in today's lesson, we're going to look at impulse. All right, let the games begin. When a net force acts on a body, it will result in an acceleration which alters the motion of the body. A large net force will cause a large acceleration than a small net force. The total change in motion of the object can be the same if the large and small forces act for different time intervals. The combination of the force and time that it acts is a useful quantity which leads us to define impulse. Impulse is the product of the net force and the time interval for which the force acts. Right. However, from Newton's second law, we know that F net is equals to change in momentum over change in time. Therefore, F net times change in time is equal to change in momentum, which is therefore equals to impulse. Therefore, we can define the impulse momentum theorem as impulse is equals to change in momentum. Impulse is equal to the change in momentum of an object. From this equation, we see that for a given change in momentum, F net times delta t is fixed. Thus, if F net is reduced, change in t must be increased, meaning that a smaller resultant force must be applied for longer to bring about the same change in momentum. Alternatively, if the change in time is reduced, meaning the resultant force is applied for a shorter period, then the resultant force must be increased to bring about the same change in momentum. The graphs below show how the force acting on a body changes with time. So you can see there. And the graphs below show how the force acts on a body changes with time. The area under the graph shaded in represents the impulse of the body. Yeah. Now let's look at the worked example. A 150 Newton resultant force acts on a 300 kilograms trailer. Calculate how long it takes this force to change the trailer's velocity from 2 meters per second to 6 meters per second. In the same direction, assume that the forces act to the right, which is the direction of motion of the trailer. Step number 1, identify what information is given and what is asked for. The question explicitly gives the mass of the trailer, the trailer's initial velocity, the trailer's final velocity, the resultant force. We are asked to calculate the time taken to accelerate the trailer from 2 to 6 meters per second. So from Newton's second law, we know that F net delta t is equals to change in momentum, which is equals to mvf minus mvi, and change in t is equals to m over f net, fv minus vf minus vi. Thus, we have everything we need to find delta t. So if we substitute, the change in time is going to be 8 seconds. So it takes 8 seconds for the force to change the object's velocity from 2 meters per second to the right to 6 meters per second to the right. Example number 2. A cricket ball weighing 150 grams is moving at 54 kilometers per hour towards a batsman. It is hit by the batsman back towards the bowler Oh, it is hit by the batsman back towards the bowler at 36 kilometers per hour. Calculate the ball's impulse and the average force exerted by the bat if the ball is in contact with the bat for 0.13 seconds. So firstly, identify what information is given. So the question explicitly gives the ball's mass, its initial velocity, final velocity, time of contact, and we are asked to calculate the impulse. Impulse is equal to change in momentum, which is F net delta T. Since we do not have the force exerted by the bat on the ball, we have to calculate the impulse from the change in momentum of the ball. Now, since change in momentum is mvf minus mvi, we need the ball's mass, initial velocity, and final velocity, which we are given. Step 3, Step 2, convert to SI units. So if we do that, we should get 0.156 kilograms. Next, we change units for the velocity to change the direction from the batsman to the bowler as the positive direction. Then the initial velocity of the ball is negative 50 meters per second, while the final velocity of the ball is the moment 3.9 to the ball. This is just the change in momentum of the ball. 3.9 kilograms meters per second in the direction from the batsman to the bowler. Then to determine the average force by time, and then that is going to give us 30 Newton in the direction from the batsman to the bowler. Right now, let's analyze the force graph. Analyze the force versus time graph provided and answer the following questions. What is the impulse for the interval 0 to 3? 0 seconds to 3 seconds. So you know that you obviously need to calculate the area. Just to determine both impulse and change in momentum from it. We know that the area under the graph is the impulse, and we can relate impulse to change in momentum with the impulse momentum theorem. We need to calculate the area under the graph for the various intervals to determine impulse, then work from there. So we need to times height second. The impulse is 4.5 Newton second in the positive direction. Now from 3 to 6, so the impulse is 4.5 in the negative direction. We just add what we have there. So the seconds is exactly opposite to the impulse in the second 3-second interval, making the total impulse for the first 6 seconds 0. From the impulse momentum theorem, we know that Newton seconds. Then from 6 to 12, we need to calculate the area of the shaded portion under the graph. This is divided into two areas from 6 to 12 and 12 to 20, which we need to sum to get the total impulse. From 6 to 12, it's negative 18, 12 to 20, 60 Newton. Then if we sum those in, sharp. Okay, let's look at another worked example from a previous past paper. A patrol car is moving on a straight horizontal road at a velocity of 10 meters per second east. At the same time, a thief in a car ahead of him is driving at a velocity of 40 meters per second in the same direction. Velocity of the patrol car relative to the ground, and then velocity. Okay, question 1 and 2 from the original version in 2011 paper are no longer part of the curriculum. Anyway, let's look at them. While traveling at 40 meters per second, the thief's car of mass 500 kilograms, moving at 20 meters per second. After the collision, the car and the truck move together. State the law of conservation of linear momentum. The thief's car immediately after the collision. Research has shown that forces greater than 85,000 Newton during collisions may cause fatal injuries. The collision described above lasts for 0.5 seconds, determined by means of a calculation whether the collision above could result in a fatal injury or is conserved or does not in the absence of external forces. Then taking to the right as positive, time after, blah, blah, blah. So that's the answer. Then from there is equals to negative change in momentum of the track. Then if you substitute, you should get that answer. Then question 3. Question 3. The first 1,000. So yes, the collision is going to be fatal. Sharp. There are different ways of calculating that, but yeah, we won't go there. Sharp. All right, guys. So this is a short exercise. Please pause the video and try it on your own. I mean, it wouldn't hurt to do that. Number 4 or 5, number 6. Yeah, then for more questions, you can go to action. A very important application of impulse is improving safety and reducing injuries. In many cases, initial velocity. This means there is a certain specified change in momentum. If the time during which the momentum changes can be increased, then the force that must be applied will be less, and so it will cause less damage. This is the principle behind arrestor beds for trucks, airbags, and land on the ground. Airbags are used in motor vehicles because they are able to reduce the effect of the force experienced by a person during an accident. Airbags extend the time required to stop the momentum of the driver and passenger. During a collision, the motion of the driver and passenger carries them towards the windshield. If they are stopped by a collision with the windshield, it would result in a large force exerted over a short time in order to bring them to a stop. If instead of hitting the windshield, the driver and passenger hit an airbag, then the time of the impact is increased. Increasing the time of the impact results in a decrease in the force. Right, that's according to Newton's second law there. Therefore, if T is increased for a constant change in momentum, force on body is reduced. Now, padding as protection during sports. The same principle explains why wicket keepers in cricket use padding gloves or why they are padded mats in gymnastics. In cricket, when the wicket keeper catches the ball, the padding is slightly compressible, thus reducing the effect of the force on the wicket keeper's hands. Similarly, if a gymnast falls, the padding compresses and reduces the effect of the force on the gymnast's body. Arrestor beds for trucks than the road. Trucks use these when they have to make an emergency stop. When a truck time is increased, this decreases the force and causes the truck to slow down. Follow through in sports. In sports where racket and bats are used, like tennis, cricket, squash, badminton, and baseball, the hitter is often encouraged to follow through when striking the ball. High-speed films of the collisions between bats, rackets, and balls have shown that following through increases the time over which the collision between the racket and ball occurs. This increase in the time of the collision causes an increase in the velocity change of the ball. This means that a hitter can cause the ball to leave the racket faster by following through. In these sports, returning the ball with a higher velocity often increases the chances of success. Crumple zones in cars. Another safety application of trying to reduce the force experienced is in crumple zones in cars. When two cars have a collision, two things happen. The cars bounce off each other or the cars crumple together. Which situation is more dangerous for the occupants of the car? When cars bounce off each other or rebound, there is a large change in momentum and therefore a larger impulse. A larger impulse means that a greater force is experienced by the occupants of the cars. When cars crumple together, there is a smaller change in momentum, and that the occupants of the cars experience a smaller force. Car manufacturers use this idea and design crumple zones into cars, such that the car has a greater chance of crumbling than rebounding in a collision. Also, when the car crumbles, the change in the car's momentum happens over a long time. Both these effects result in a smaller force on the occupants of the car, thereby increasing their chances of survival. Okay. Alrighty. So more calculations, more calculations. Please. Now let's summarize the chapter. Newton's second law. The resultant force acting on a body will cause the body to accelerate in the direction of the resultant force. The acceleration of the body is directly proportional to the magnitude of the resultant force and inversely proportional to the mass of the object. Newton's third law. If body A exerts a force on body B, then body B will exert an equal but opposite force on body A. The momentum of an object is defined as its mass multiplied by its velocity. Momentum of a system. The total momentum of a system is the sum of the momenta of each of the objects in the system. The principle of conservation of linear momentum states that the total linear momentum of an isolated system is constant, or in an isolated system, the total momentum before a collision is equal to the total momentum after a collision or explosion. An elastic collision means that both total momentum and total kinetic energy are conserved. In an inelastic collision, only total momentum is conserved, but total kinetic energy is not conserved. Impulse is the product of the net force and the time interval for which the force acts. The law of momentum, the applied resultant force acting on an object is equal to the rate of change of the object's momentum, and this force is in the direction of the change in momentum. The impulse momentum theorem states that the impulse is equal to the change in momentum. All right. So these are your physical quantities. And then more work is given there. Exercise 2.7. Mm-hmm. 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 Sharp. I think it's going to be important for me to go through these questions. Yeah, they look very interesting. Yeah. Yeah. Yo, and quite a lot. All right, guys. Thank you so much for taking the time to watch this. So in the next video, I'll go through those exercises. Then after that, we're going to start a new topic, vertical projectile motion in one dimension. Thank you.